Hi, Academy students. Today we are looking at standard SC3 1A, A1, sorry. Anyhow, we're looking at balancing chemical reactions. In chemistry, we actually have 6 different types of reactions that we will play with and learn how to work with. That's synthesis, decomposition, single replacement, double replacement, neutralization, and combustion. But today we're just looking at balancing reactions. And balancing reactions center around the law of conservation of matter. Basically, the law of conservation of matter says that matter cannot be created or destroyed. It only changes forms. So the amount of stuff that I start with has to equal the same amount of stuff that I end up with. It's just in a different arrangements. Now, in order to comply with the law of conservation of mass, the amount of products have to equal the amount of the reactants. So if I started with 5 grams of reactants, I'm going to end up with 5 grams of products. In chemistry, frequently we start with word equations. Now, right now, I'm going to actually be giving you the skeleton equation, the equation with just the letters and the numbers. But if I were to give you the word equation, you would have to use your nomenclature rules to turn the words into formulas, and then count your number of atoms and add coefficients to balance each. Now, our coefficients are those big numbers that we place in front of a chemical formula in order to balance it. A balanced chemical equation is a chemical equation that complies with the law of conservation of mass. The number of atoms of each element is equivalent on either side of the reaction. Now, we will eventually get to a point where we are starting with a word equation, but for right now, I'm going to give you the skeleton equations. And your skeleton equations are the equations that just have the letters and the subscripts. No coefficients have been added yet. Now, when we're looking at balancing atoms, we got to remember how to count atoms. And this was something we learned in the last unit when we were calculating molar mass. The things you do need to remember is that if you have a subscript outside the parentheses, it multiplies everything that is inside the parentheses. It distributes all the way in. Coefficients will end up multiplying everything that is behind it. But those two things actually end up multiplying each other. So if I'm looking at my example A, notice I don't have anything besides that Cu. So remember, we have our invisible 1 if there's nothing beside there. There's no parentheses, so therefore I only have 1 copper. But my NO3 is in parentheses. Therefore, I have to distribute this 2 within. So I have 2 nitrogens and 6 oxygens. Same thing with the ammonium phosphate. This 3 that is outside the parentheses distributes in and multiplies both the subscripts, my visible 4 and my invisible 1. When everything's distributed out, we have 3 nitrogens, 12 hydrogens, 1 phosphorus, because there's no parentheses here, nothing to distribute, and 4 oxygens. Now, as we're adding coefficients, these big numbers in front are my coefficients, and they multiply everything immediately behind it. Anything that is in that compound is multiplied by that coefficient. So when I add a 3 in front of my copper 2 sulfate, I end up with 3 coppers, 3 sulfurs, and 12 oxygens. With my copper 2 nitrate, I end up with 2 coppers, 2 times 1. And then for my nitrogens, 2 times 2 times 1, so 4. And for my oxygens, 6 times 2, 12. You kind of see how this particular process works. Remember, you are allowed to use a calculator if you and mental math are not best friends. Now, I like a nice simple procedure for balancing equations. This is how I go about balancing an equation. And I know some of you guys have had physical science in high school, and your physical science teacher might have done it differently. If they did, and you remember how to do it, as long as it works, I'm okay with you using that process. So you're first by getting your skeleton equation. Now, right now, I'm going to be giving you this. Next, you list all of your elements. I always list them under the arrow so that I only have to write them one time. This is what I call your element inventory. Once you've listed all your elements, you count the number of elements on each side of the reaction. This gives you your initial count, and you see which elements don't match. The ones that don't match, you ask yourself which side needs more. Once you determine which side you need more, you're going to multiply so that you can make the number of atoms on each side equal. Think least common multiple. So if I had a 2 and a 4, I'd multiply one side by 2. If I had a 2 and a 3, my least common multiple would be 6. So I'd have to multiply by 3 and 2. Now, there are some general things that will help make your life a little bit easier. First, start by balancing one substance at a time. Add one coefficient and then recount. Your general rule of thumb when you're balancing is to save your H's and O's until the end. Your hydrogens and oxygens tend to be in multiple places and they work themselves out. Next, start by balancing the most complex thing. If you have an element that is just sitting all by itself, wait until the end to balance them. As you add your coefficients, you're going to recount and list the new number of atoms. So let's see these steps in practice. I have a reaction. Of zinc with hydrosulfuric acid reacting to form zinc. Oh, that wasn't the best one to use, whatever. Let's not use zinc. There we go. There we go. So I have aluminum and hydrosulfuric acid reacting to produce aluminum sulfide and hydrogen gas. This is the skeleton equation. This right now is going to be given to you. I list my elements under the arrow. So I've got aluminum, hydrogen, and sulfur. Next, I count the number of atoms of each element on each side of the arrow. I like doing this under the arrow so that I have that nice, pretty dividing part. So I count on the left, I've got 1 aluminum, 2 hydrogens, 1 sulfur. On the right, 2 aluminums, 2 hydrogens, 3 sulfurs. My general rule of thumb says I don't start with my hydrogen. I leave my hydrogen and my oxygen until the end. Well, hydrogen is already balanced, so I'm not going to need to start with it at all. Next, I look at my aluminum or my sulfurs and I decide who I want to start with first. So I'm arbitrarily picking aluminum. In order to balance my aluminum, I ask myself which side needs more. Well, I need more aluminums on the left side of my reaction, the reactant side. Therefore, I add my coefficient on the left side of the equation. What times 1 will give me a 2? Well, my least common multiple is 2. So I multiply aluminum by 2. My aluminums now match. My hydrogens still match. So now I move on to my sulfurs. My sulfurs, I have 1 and 3. My least common multiple is 3. So I know I'm going to need to multiply by a 3 in order to get them to match. I add a 3 as a coefficient here in front of the compound that contains the sulfur. I have to put it in front of the compound and not in the middle of the compound. That 3 multiplies everything behind it. So multiplies the hydrogens and the sulfurs. I now have 3 sulfurs and 2 times 3, 6 hydrogens. We fixed the sulfur, but in the process of fixing the sulfur, we broke the hydrogen. That happens sometimes. So now let's go and fix our hydrogen. I ask myself which side needs more. Well, this time the product side is going to need more. I have a 2 and a 6. My least common multiple is 6. So what times 2 will give me 6? Well, 3 times 2 will give me 6 hydrogens. My inventory tells me how many atoms of the elements I have. I go through and I double check, make certain that everything is balanced, and I notice that I didn't put a number in front of this aluminum sulfide. Well, when you don't put a number, it's considered an invisible 1. You can write the 1, but you don't necessarily have to write the 1. But we have 1 molecule, 1 piece of aluminum sulfide to 3 hydrogens, 2 aluminums on the reactant side, and 3 hydrosulfuric acids. Now, we rinse and repeated steps 4 through 7 multiple times. So let's look at a second example. I've got the synthesis of ammonia. Nitrogen and hydrogen come together to react to produce ammonia. I list my elements. Step 1 was the equation. Step 2, list the elements. Step 3, do your counts. No number is an invisible 1. Remember, y'all can always write it if you want. Then I ask myself, which element do I want to start with? Well, general rule of thumb, save your H's and O's until the end. So I'm going to start with my nitrogen. Which side needs more? Well, my product side needs more nitrogen. So therefore, my coefficient is going to go on the right side. What times 1 will give me 2? I want a 2. So 2 times 1 gives me 2. I'm multiplying in all this up top, and my element inventory, this thing below the arrow, is just keeping track of how many atoms of each substance I have. So that 2 not only changes the nitrogen, it also changes the hydrogen. 2 times 3 is 6. So we fixed the nitrogen, we broke the hydrogen. In order to fix the hydrogen, I have 2, I have 6. My least common multiple is 6. That means I'm going to have to multiply by a 3. I put a 3 in front of the substance that has the hydrogen. 3 times 2 gives me 6. I don't have anything in front of the nitrogen, therefore it is an invisible 1. 1 nitrogen and 3 hydrogens react to produce 2 ammonias. Now, even though both of these contain fairly simple reactions, it doesn't really matter the type of reaction it is. It doesn't matter how complex it seems, the process is still the same. Now, what we hadn't seen yet is when the same element appears on both sides of the arrow, Badness rings, on one side of the arrow multiple times. So notice how I have oxygen in multiple places. Since oxygen is on the right-hand side of the reaction 3 different times, I'm going to have to add all the oxygens together when I go to do my initial count. This is one reason why we end up doing our oxygens and our hydrogens till the end, especially when you're looking at a combustion reaction. Now, this particular reaction, we've got our sodium bicarbonate decomposing into sodium carbonate, water, and carbon dioxide. My initial count on the left is fairly straightforward. It's my product side that gets a little complicated. So 2 NAs, hydrogen is 2, carbon, well, they're in 2 places. I always like to underline it to remind me to keep them together. So I've got 2 carbons, and my oxygens, I've already underlined, is in 3 different places. So 2 plus 1 plus 2 gives me Badness Reigns. That was 3 plus 1 plus 2 gives me 6. So I look and I see what doesn't balance. Well, nothing balances. My general rule of thumb says to leave my H's and O's until the end. I'm going to start with my Na. Well, in order to fix my sodium, I know I need more sodium on the left side, my reactant side. My least common multiple is 2. So I put a 2 here. That not only changes the NAs, but it changes everything in that sodium bicarbonate. So I now not only have 2 NAs, I have 2 H's, 2 C's, and 6 O's. Oops. Now, it doesn't matter how you list the elements. As I said, you may have seen it done slightly different in a previous class. The goal of balancing your equations is that you actually get it so that they balance. So some physical science teachers have you list them both on the left and the right. I do discourage this unless you're in the habit of always listing them in the same order. It's really, really easy for students to mix them up. But no matter how you go about doing it, you must show your element inventory. Your count, how many elements you have, in addition to showing your coefficients. Now, remember when you're done balancing that if there's not a number in front of there, it's an understood 1. So on my product side, since we didn't have to change anything over there, in front of each of the products, I've got a 1 as a coefficient.